Equations of Lines and Planes, Level 2. In our previous video, we introduced vector functions as a way of describing curves in a 2D plane and 3D space. Now we're going to use this knowledge to figure out how to describe the equation of a line in 3D space. Recall from your previous math courses that the equation of a line in 2 dimensions can be written in point-slope form. In order to write down the equation of a line in r², we needed to know the slope m, or angle of inclination, and a point x0, y0 that was on the line. So it makes sense that in r³, we would also need a slope and a point on the line. The slope of a line in r³ would not be a simple number as it was in r². In this case, a line in r³ will have a 3-dimensional slope. We need something that will allow us to describe a direction in r³. From our previous video series, we learned that vectors do just that, since vectors can be used to describe directions in both r² and r³. Let's see how we can use vectors to describe a line in space. Say we have a line in 3D space, and suppose that we know a point that is on this line. Let's call it P0, with coordinates x0, y0, and z0. And suppose that vector v, with components a, b, c, is some vector that is parallel to line L. This vector is usually referred to as a direction vector, and the components a, b, and c are called direction numbers. Note that vector v does not need to be in standard position and can have a completely different initial and terminal point. We only require vector v be parallel to the line. We will also let point P with coordinates x, y, z be an arbitrary point on the line. Next, let's represent point P0 and point P by using position vectors. Let's call them vectors r0 and vector r respectively. Finally, we can draw one last vector that starts at point P0 and terminates at point P. Let's denote this vector as vector A. Notice from this diagram that vector r can be written as a sum of vector r0 and vector A. Recall from a previous video that the head-to-tail method, or triangle law, was used to add vectors. Also notice that both vector A and vector v are parallel. This means that vector A is equal to a constant multiple of vector v. For this scenario, let's use the constant t instead of the usual constant c that we used in previous videos. This expression for vector A can now be substituted into the vector expression for vector r. Doing that, we obtain the following. This is called the vector form of the equation of a line. The only part of this equation that is not known is the variable t. The variable t is known as a parameter, and will play the role of a scalar, a real number. Values assigned to the parameter t will generate position vectors r with terminal points located on the line. In other words, as t varies, the line will be traced out by the tip of vector r. Notice that the expression t times vector v will be a vector that lies along the line, and it tells us how far from the original point P0 we should move. If t is positive, we move away from the original point, in the direction of vector v, since a scalar multiple of a vector scales the magnitude of vector v without affecting its direction. And if t is negative, we move away from the original point in the opposite direction of vector v, since scalar multiplication by a negative number flips the original vector in the opposite direction and scales the magnitude of the vector. As t varies over all possible values, we obtain the complete graph of the equation of a line in 3D space. There are several other forms of the equation of a line that can be obtained from this vector form. To obtain an alternative form, let's start with the vector form and rewrite it. We're going to denote vector r in component form as x, y, z. We will also denote vector r0 in component form as x0, y0, z0. Lastly, we will denote vector v in component form as a, b, c. Doing that, we obtain the following. Next, we simplify the right side of the vector equation by multiplying the parameter t by the components of vector v. We then add the components of this vector with the components of vector r0. Doing that, we obtain the following alternative form. Recall from a previous video that two vectors are equal if and only if corresponding components are equal. This means that we can equate the corresponding components of this vector equation to obtain the following. X equals x0 plus a times t, y equals y0 plus b times t, and z equals z0 plus c times t, where t is an element of the real numbers. These sets of equations are called the parametric form of the equation of a line through the point P0 with coordinates x0, y0, z0, and parallel to vector v with components a, b, c. Each value of the parameter t generates a point x, y, z on line L. Notice that this form is just an extension of the parametric equations that you covered in your Calculus 2 Integral Calculus course. The only difference is that we are now working in 3 dimensions instead of 2 dimensions. Notice that in the vector form of a line, values of the parameter t would generate position vectors in standard form that terminate at a point on the line. In the parametric form, values of the parameter would generate the coordinates of a point on the line. In general, if a vector v with components a, b, c is used to describe the direction of a line L, then the numbers a, b, and c are called direction numbers of L. Since any vector parallel to vector v could also be used, we see that any 3 numbers proportional to the direction numbers a, b, and c could also be used as a set of direction numbers for line L. In other words, the vector equation and parametric equations of a line in space are not unique. If we change the initial point or the parameter or choose a different parallel vector, then the equation of the line also changes. So keep this little detail in mind when you're writing the equation of a line in R-cubed. There is one more way in which we can write the equation of a line in space. We can find an alternative form by eliminating the parameter t from the parametric equations of a line. If we assume that a, b, and c are all non-zero numbers, we can solve each of the parametric equations for the parameter t. We can then set all of these expressions equal to one another. Doing this, we end up with the following expression. This is called the symmetric equations of a line. Notice that the numbers a, b, and c that appear in the denominator are the direction numbers of line L. Recall that these are the components of a vector parallel to line L. If one of the direction numbers happens to be equal to 0, we can still write down the symmetric equations. For example, if the direction number a is equal to 0, then the parameter t will not exist for x. So we will only solve for the parameter t in the parametric equations that contain y and z. We then set those parametric equations equal to one another, and acknowledge the parametric equation for x as follows. X equals x0. This means that line L will lie in the vertical plane x equals x0, since the x-coordinate is constant and does not vary. If we happen to know 2 points on the line, we can rewrite the symmetric equations of a line by noticing that the direction numbers of line L through the points P0 with coordinates x0, y0, z0, and a second point P1 with coordinates x1, y1, z1 is x1 minus x0, y1 minus y0, and z1 minus z0. And as a result, the symmetric equations of line L can be written as follows. Usually, we use the form that contains the direction numbers a, b, and c when solving problems in multivariable calculus. At times, we need to describe a line segment and not an entire line in space. Similar to piecewise defined functions, where we define functions on a particular interval of a function's domain, we can use a similar concept to describe a particular section of a line in space. We can generate the equation of a line segment in 3D space by using the vector equation of a line. If a line segment has an initial point represented by the position vector r0 and an endpoint represented by the position vector r1, then we can generate a direction vector by subtracting these two vectors. In this case, the direction vector v will be equal to r1 minus r0, and so the vector equation can be written as follows. We can then distribute the parameter t and group together like terms, factoring out the common vector r0. Doing that, we obtain the vector equation of a line segment from r0 to r1. Notice that the values of the parameter t are restricted and are defined from t equals 0, the initial point of the line segment, to t equals 1, the endpoint of the line segment. Alright, now that we have covered all the different ways to write the equation of a line in space, we will start going over a couple of examples in our next video and see how we can use the various equations of a line to solve problems in multivariable calculus.